We are recording. All right, so last time was a little rushed, but we covered how to represent um, decimal numbers using binary number representation, and that's a means of representing these numbers in digital logic. And then we very quickly covered computer elements, so different logical structures that we can build up to perform discrete functions within the scope of a computer. And to briefly go over that again, we have a structure that can persistently store one bit of information that we can chain together to form memory. We have something that can switch between different signal lines based on an indexing bus. We have a structure that can perform one bit arithmetic, so specifically one bit addition, which we can then chain together to do unsigned addition. And then we ended out with a system that we can use to count up based on the state of a clock signal. So all of these structures become very useful when we actually start talking about how computers themselves function. So that's what we'll do today. So to kick it off, we kind of need a formal definition of a computer now that we have all of the underlying theory necessary to kind of think about it. So a computer is any machine that stores, retrieves, and processes data automatically. And another way of putting that is you can tell it what to do, start it, and it will do so without further input. So this means you can do sequences of arithmetic or logical operations, and again, it does so without additional input. So to do this, we basically need to divide the computer into four main structures. Memory, which we've talked about, stores and retrieves data, and also instructions to command the computer. The processing unit, which carries out the operations. Input and output, which is how the computer actually interfaces with the outside world. And the control unit, which kind of correlates everything together, routes and interprets instructions sent to the computer, and tracks operation. When we talk about a CPU for a modern computer, usually we're talking about the control unit and processing unit together because those form the core logical operation of the computer. And everything else is a separate component. So how we actually organize these four components can vary. And there are two principal architectures for how we can build up modern computers. The first of these architectures that was actually developed was the von Neumann architecture, which is also known as the Princeton architecture. And in that, the memory for program data, so the collection of instructions that you're giving to the computer, and the data that it's operating on, or the data where it's storing information, are both in the same memory area. So the binary numbers that you're trying to store and the commands that you're trying to store are both in the same place. The CPU would then operate on that information, taking in instructions and decoding the information that's stored as data, and then either transforming some input or giving us some output, or both. The contrasting architecture is the Harvard architecture, which just chooses to split up where you store instructions versus memory, or versus data in memory. So these could be entirely separate physical memory devices, or this could be kind of a virtual break between a section of the memory that's designated as data only versus program only. And today, the most common thing to do is actually a modified version of this Harvard architecture. So they can, like I mentioned, be in the same memory area, but there are still two buses that communicate data versus instructions. And typically the memory is specifically designed to allow these two parallel accesses. So again, the programming unit here, they're calling it the ALU because they're very similar, and we'll get into that. But we have the processing unit, the control unit, and I/O, and the control unit kind of shuttles things, shuttles information from the instruction and data memory. So now we can actually get into how each of these blocks are operating. So memory, as we've mentioned, is a collection of bit fields. Specifically, their uniform length, and you can index into them by the field called an address. So if you'd imagine, we have a contiguous section of memory, which is basically just, you can think of it like a table almost, but it's effectively a one-dimensional table, unless you choose to assign meaning to the memory sections such that there's multiple dimensional data stored in there. But so it's, we have uniform length bit fields. So in this case, I'm representing fields that are 8 bits long. And so there are contiguous areas of 8 bits. So in the electrical implementation for this memory, you would have effectively just a bunch of registers. And how you choose to access those registers is by addressing them by their bit length. So we have this first address that represents the first 8 bits of data, and so on. So the second address represents the next 8 bits of data. You can look at this as if it's 32 bits for these 4 memory areas, except you still have to do the addressing on the native bit length of the memory. So formally, this memory contains 2 to the k, where k is the bit length, by m, which is the number of addresses, sets of bits. And basically, we can use this to either store our binary numbers or storing bit fields and using those bits to do things. But the main point is this gets us, again, persistent memory. So the ability to store information in the long run. So the simplest form of memory is random access memory. And that's what your CPU uses to load and store data that it's operating on at runtime. It is a form of volatile memory. So when the power is cut to your computer, your RAM is basically wiped, unless your computer does something special to store your RAM in another section of non-volatile memory. Most RAM contains 2 registers that are used to interface with it. So you have the memory address register. So that's a dedicated set of bits that indicates the address that you're interested in when working with the memory. And the memory data register, which contains either the value that you'd like to store or the value that you're retrieving from the memory. And that's the interface that the computer actually has with the sections of memory. You're not actually connecting electrical signals directly to these bit fields. So there are also some signal lines, like to command the memory to do some kind of operation. So if you have a store signal line, the memory block will look at the memory address register, index into that set of bit fields, and then store the memory data register contents there. And likewise, if you do a load operation, you first set the memory address register to a specific value. The memory block will interpret that and send the data that's at the targeted register to the memory data register. So again, everything is interfacing using these 2 registers to access memory. There are other kinds of volatile memory that we can talk about, like cache and DRAM, and these just have different performance properties. So like cache is intended to sit much closer to the machine than RAM. So instead of doing conscious memory access operations, oftentimes cache will be automatically wired to store the last X number of instructions or store the last X number of fetches from random access memory. And that just makes operations much faster. It's a means of optimizing your performance. DRAM is also very similar. It just sits at a different level of optimization. But fundamentally, they still work very similarly to good old RAM in that you are just loading and storing data. Oh yeah, and program memory is typically implemented as non-volatile memory. So you, when the computer boots up, it typically grabs all of the information that it's going to need to operate on, sticks that either in RAM or some other non-volatile memory, and then operates the set of instructions from that non-volatile memory. And that's mainly because, yeah, so it's stored as non-volatile memory, fetched and loaded into volatile memory at runtime. The reason it's stored as non-volatile memory is so that you can have a persistent means of having the computer behave the same way when it starts up, but it's loaded into volatile memory at runtime because non-volatile memory takes longer to access. Usually stores take longer. And if you're doing operations in the program memory area, which it's possible, then you don't want to be touching non-volatile memory when you do that. So the next main block within the computer is the processing unit, and that basically covers all of the arithmetic and digital logic that we've been talking about. So the ALU is the main component within that processing unit that does all of these logical operations, including all of the arithmetic operations that we did on binary numbers, and a couple of new operations, which I'll talk about. But the main thing to know about the ALU is that it only operates on integer values. So no floating point operations happen in this block. But the gist of operation is you pass it. So these integer operands, the result, and I think the opcode are all data buses. So they're collections of bit signals that have a specific length. So these carry binary numbers specifically for the ALU. And you set these signal buses to be the values that you want to operate on, so A and B. Opcode is a set of signals that dictates which of the operations you're going to do on those two integer operands. So this opcode could represent the add function. It could represent a subtraction, a multiplication, any of the arithmetic operations. The opcode could also represent like a bit shift, like we talked about, a rotate, or a couple other like bitwise operations. Status is a multifunctional signal. So for instance, if we were doing something like add again, recall that we had a carry operation. So if we had done an addition using the ALU in a previous instruction, then there's going to be some kind of result for representing whether or not there's a carry value from that addition. And we could pipe that into this status signal if we wanted to. The exact formatting of what status means varies depending on the operation they're actually trying to do in the ALU. Let's see. Yeah, so the specific bit width that we have to operate on data, so the integer size here and the integer size at the result, and I think the status as well, that width is called the word size for your machine. And that's the native bit field length of the information you can work with in one operation. So if you have an 8-bit machine, that 8-bit machine, if you have a machine that has an 8-bit word size, then these integers will all be 8 bits long. And if you wanted to do integer math using a larger value, say like a 16-bit integer, then you would have to do 2 cycles of instructions to do those the operations necessary. So the word size is important for how much performance you can get out of your machine, how quickly it can get through the set of instructions you've given it. So the ALU is one structure within the processing unit, and it's handling all of this logical operation and arithmetic operation. The processing unit typically also has a bunch of registers that are multi-purpose. So I've mentioned these integer operands and the result. These are probably given their own register, depending on the implementation of your machine. But there are also typically several other utility registers that you can access that are basically temporary storage so that you don't have to access memory. Again, accessing memory is typically a longer lived operation than something like accessing a register. Depending on the ALU implementation, there could also be like supplementary data buses that can give information to certain instructions. And that's, again, something that you would store in one of these multi-purpose registers. And the registers are all the word size of the machine, naturally. So the last thing that you could encounter in the processing unit is a dedicated machine submachine for dealing with floating point numbers. And we call these floating point units. So they have internal logic to deal with specific standards for floating point numbers. So very likely that's going to be the IEEE 754 format that we talked about. And this floating point unit will handle all of the operations necessary for interpreting those numbers, doing arithmetic on them, and doing so much faster than it would take the ALU to do. The downside is you need this dedicated hardware to do those like fast floating point operations. If you don't have an FPU as part of your machine, then it's still possible to do floating point operations. You just can't have dedicated hardware to do it. So typically you'll either see an implementation that that has dedicated instructions to do floating point operations. So you'll have like a floating add. It'll still use the ALU, but the ALU will take several cycles to do that addition. Whereas for like a native integer, it would have taken maybe 1 or 2, depending on the size of the integer you're trying to do the operation on. It's also possible to emulate floating point operations in software. So when we get to how we actually program these computers, there could be like a library that exposes functions that do floating point math. And that, again, will just sit on top of the ALU. But that's kind of the last resort because if your machine has dedicated floating point instructions that work on the ALU, that's going to be faster than having to emulate that behavior via software. And that's because software needs to set addresses, it needs to fetch information. So the point being, it'll take much longer for a software implementation to get through a floating point operation than dedicated instructions, or better yet, dedicated hardware. So that's all the stuff that's typically in a processing unit. There may be other kinds of implementations for arithmetic or logical operations that doesn't fit in the native ALU. And that's if you're doing something funky, like you're trying to make a novel computer type, or maybe you want a machine that's dedicated to doing digital signal processing. So you want like vector math. That could be another addition that you'd find in the processing unit, depending on the kind of machine you're working with. But typically you can always expect there to be an ALU because that's necessary to do the rest of the computer functions. And typically there are multi-purpose registers that you can store and load information from that are much faster to access than random access memory. So that's so far we have a means of storing and loading information and a means of processing that information. We could also pipe that information in and out of our machine. So input-output is just any system that helps the computer interface with the outside world. Another way of looking at this is drawing the boundary around just the memory and CPU and saying that's your computer and everything outside of that is input-output. And that's probably how we're going to end up looking at microcontrollers, because you could have additional like computer structures outside of your main computer that perform dedicated functions. And that's precisely how microcontrollers are typically organized. And then those computer structures may interface with the outside world. But for our purposes here, we'll talk about input-output as everything outside the CPU and memory. So in a lot of cases, you'll find that the CPU has a dedicated bus that it uses to talk with anything outside of itself. And we can call this the main computer bus. I may have mentioned this before. So that bus is almost certainly going to be clocked, and that just means it's synchronized to the operation of the main CPU. And I will talk about that more as soon as we get to microcontrollers. The last main structure that you could expect in a computer is called the control unit. And this is basically where all the magic happens, because you have to route all the behavior that you find in memory, all the behavior that you find in the processing unit and I/O, and that all that routing and management happens in one location, and that's here. So the control unit was actually executing these instructions that you're giving to the computer. So you would grab information from memory, saying what you want the computer to do, and the control unit would then interpret that, configure all these electrical signals such that only the ones that are relevant to the operation are active, and clock all of the other subcomponents within the computer to have them synchronize and perform the operation successfully. So if your current instruction is an add instruction, typically the control unit will load the operands you want to work with. So you could have a dedicated add instruction that references two registers that are already loaded with information, or you can have an add instruction that says, here's a value that will never change, so you don't have to load it from memory. It's already stored as part of the program memory. Add it to some other register. And the control unit will differentiate between those two kinds of instructions that perform an addition, and make sure the ALU input operands, so these two integers, are mapped to the correct fields. So that's like switching the data bus that inputs to the ALU. But that's only one example of the kind of instruction that a control unit would manage. I think it's worth spending some time talking about what instructions actually are. So we know we're storing them in program memory, so there's some kind of bit field, but the format really matters for instructions, because that's how the computer will interpret what to do. So instructions are typically broken into opcodes and operands. For that good old add example that I've been talking about, you could have several bits in this bit field. So if 0 is the least significant bit and 15 is the most significant bit, then typically the first 3 or 4 most significant bits represent the opcode, which is the command that you're actually giving the computer to do. This is very similar to the ALU's opcode, but has an expanded set of operations that you can do. So the ALU has dedicated functions that are all arithmetic and logic. The computer can have additional functionality that you could expect by virtue of it being more complex than the ALU. So I'll talk about some kinds of instructions that you can encounter, but note that there's an opcode here. The remaining fields are all of the operands that you need to perform the instruction. It's possible that your instruction doesn't have any operands and performs some dedicated function that the computer needs to perform some special function that doesn't take any operands. Also, you could have an instruction that references certain registers in the processing unit instead of taking operands, and that's another common thing that can happen. But most likely, you're going to have something that you have to communicate alongside the instruction. So with add, it is referencing 2 registers in this implementation, and we use 3 bits to represent which register to access. So the add opcode could command the ALU to perform some operation. This implementation of add would reference some register indicated by these 3 bits as operand A, likewise for operand B, and this add can also dictate specifically which register to output to. Other implementations may vary. This is just one specific example. But bringing this back to our digital logic representation of things, this is still just a bit field. So if we assume the add opcode is like all zeros, which is almost never the case, and that the result register, operand A register, and operand B registers are 0, 1, and 2, then you would represent this in binary as something like this big string. So that's what's physically stored in program memory, is just this, which means we need to understand which bits are assigned to which opcode and which bits represent like the result register, register number 2. The operand A register would be the next 3 bits, and so on. So this visual representation here is just a means of identifying the format that's actually stored in this bit field. Within the control unit, you take these instructions and interpret them. So the computer is hardwired to understand that these 4 bits are the opcode. So it'll typically do some kind of like multiplexing operation where you'll have, if you have 2 different kinds of add operations, you could have like 2 different opcodes for and maybe the computer recognizes that when this first bit is changed, it's the second kind of and. So when the computer loads this big string, it has to parse through what each of these bits signifies within the context of the instruction. To do so, it uses 2 different registers. The first one's the instruction register, and when it loads information when the control unit loads information from memory, so this big string, it'll dump it to the instruction register. And this is probably the most critical register in the whole machine, because it's the one that is split off into all of these control signals that the control unit uses to route the instruction appropriately. The next most important one is the program counter, and the program counter stores the address of the instruction that you're trying to operate on. So back when we talked about memory, if this is our program memory area, this data holds our instruction, and it's located at some address. The program counter will contain that address and dictates which instruction we load next. So really, operation within the control unit is just a sequence of instruction loads. Let's see. Is the opcode part of assembly level programming? Yes, and I'm about to get to that at the end of today. So the control unit sequentially loads instructions, operates on them, puts the output somewhere, and repeats this process ad infinitum while the machine is still active. And the instruction register is the temporary location it uses to parse that information. So typically when the computer is operating, you'll see the program counter just increment over time. And that's because the control unit will parse one instruction and move on to the next one. So you'll see the program counter, if you looked at it as if it were a binary number, it would be ticking up 1 every time a new instruction is loaded, with some exceptions. So it's possible to change the program counter value with certain instructions that are typically found in all machines. And those 2 instructions typically are known as branching instructions or jumping instructions. So with branching, when you're trying to set the program counter value, typically you want to do so on some kind of condition. So that might be the result of your latest add. So if the add produces a 0 value, you want to evaluate that. And if the result of the add is actually 0, maybe you want to branch on that condition. Or you could alternatively branch when it's not 0 or equal to some specific number. The point being, when you branch, you change the natural flow of how you would be loading an instruction. So instead of just incrementing the program counter by 1, your branch can specify a new address to load instead. And the reason it's known as branching is particularly because there are 2 paths that you can take at any branch operation. You can increment the program counter and do nothing, or you can move to this new address and load instructions from there instead. So that fork is the reason we call it a branch. Computer science really likes tree analogies. So we look at it like the branches of a tree split from a trunk. The other kind of operation is known as jumping. So jumps are non-conditional. So if you have a specific address where you have a sequence of instructions that you want to repeat, or maybe it's a set of instructions for special conditions, you could set an address register that will contain where to jump to and jump there immediately. So again, the main difference between branching and jumping is that branching depends on some conditional result, and jumping is instantaneous. So to actually interpret these instructions and increment the program counter, to do all these operations successfully, the computer needs to be able to repeat this operation. So there's actually a finite state machine that we can use to represent this operation, and it's called the instruction cycle. It's very simple. It's a sequence of states, so there aren't branching states here. The computer just does this set of operations until it's powered off, and that is fetch information from memory. So specifically, it loads the next instruction according to the value of the program counter. And typically, this fetch stage will automatically increment the program counter. And that's so that we don't have to worry about it programmatically later on in the cycle. So the instruction register is loaded to contain the value that indicates what the next operation should be. And the program counter is incremented by 1. The next step is the decoding step, and that's where the control unit takes the value that's held in the instruction register, determines what the opcode signifies, and then routes all of the remaining operands and signals according to what that opcode signifies. Typically, if a memory access is required, the control unit determines what addresses are necessary. So for this example up here, these 3 bits aren't enough to specify an address. So if we have like a result, if we have a register that contains our address, the decode stage will go to that register, pull the address value, and then store it somewhere that it's used to actually index into that address. So if we had a different opcode that was working with some long form information that we'd need to fetch from memory, we could have one of these register values contain the address in memory to access. And this decode stage, again, would look at the result, or look at the address register, fetch its value, and assign the signals to the memory data register and the memory address register as necessary when accessing memory. So that happens here. And then likewise, if any of the operands are stored in memory, or in registers instead of memory, then they just fetch the registers directly. So again, this is all of the signal mapping from the control unit is taking all of the signals that it's receiving from program memory, and then either routing those signals to the ALU to operate on directly, or maybe routing information to data memory. Say you wanted to store a value that's in a register, you would take the contents of the register, wire that register to the data bus for the memory data register, and then set the memory address register to the value of where you want to store that information, perform the store, and return. And that's all the routing, the assignment of signal lines according to what the operation intends. That's decode. Execute is where the control unit sends those command signals. So you can set up all the routing, but it doesn't actually happen until the control unit sends like a signal line to the external device that's going to be doing the operation. So the ALU needs to be told to operate. And so there's usually a dedicated signal line for like ALU start doing your thing. Likewise, if you're accessing something like the IO bus, so the computer bus, that's a clocked operation. So you can set up all the routing, and then to actually have the information transmitted over the computer bus, you would need the control unit to start sending out a clock signal to clock each of the bits that's going to be sent on that IO bus. And that happens during this execute stage. So the control unit first needs to determine all the data that it's working with. So raw addresses, values, like register information, and connect those to the correct position where the information will be used, and then actually send that information and make sure it's interpreted correctly by the target device. So by the target like sub-computer structure. And then it just repeats. So after the execution, it may store the result of that execution somewhere if it's a calculation. Usually there are also some of those registers in the processing unit that are dedicated to determining the conditions of the results of the executed instruction. So like if there's an error in the operands into the ALU, that'll be stored as a condition in a register somewhere that the machine exposes, and that register value will be updated after the execute stage completes. We can then use that condition or set of condition registers when we perform our next operation. So the entire gist of this cycle is this is the machinery that lets us interpret and execute instructions automatically, assuming we have our sequence of instructions stored in memory. So this is a really simplified version of the instruction cycle. Typically, there are instructions that allow you to like skip sections of this. So I can't really think of anything that skips decode, but there may be an instruction that like resets the condition registers. So the execute stage would be really short for that. Decode is typically broken into a couple stages of like dealing with memory, and for instructions that only work on registers, then you don't necessarily need to use that stage or substage. But point being, this gives us an overview of how it can happen. Typical implementations will be more complex than this. So looking back, we now have a full machine that can store instructions to operate on, can store data to operate on, can interface with the outside world and other machines using an IO bus, can interpret instructions and compute numeric values as well as logical values using the processing unit, and does so in an organized manner that is very deterministic via the control unit. So this is like the gist of what a computer is. And anything on top of that is either an extension that gives improved performance or some new kind of functionality. But typically, any computer that you access will have these 4 blocks that perform these functions. One kind of complexity that we could see on top of this implementation is parallelizing instruction operations. So I mentioned this is a very simplified version of the instruction cycle, and reason being is we're assuming that only one instruction is in this pipeline at any given time. Certain machines, certain implementations do have the ability to store and load multiple instructions at a time. You can also like fetch from memory in parallel. but these are all just means of improving the performance of the machine. So like I mentioned, optimizations on functionality. And I'm not really going to get into it because typically that only matters for people who are really looking to wring all the kind of performance they can out of their machine. And right now we're just trying to understand how the machine operates. So this entire time, and as Nicole mentioned, I've been hinting at how we actually program this device. What actually matters to us, the engineer who's trying to achieve something with this computer. So now we'll talk about the programming interface. Let's see. So instructions are the main method of communicating what your computer needs to do. And I/O is the method that the computer uses to interface with other systems and the outside world. So those are our two main interfaces for this device. I/O, which does all of your computer's interpretation of the outside world, and the set of instructions that we can give the computer ourselves. So that set of instructions is called the instruction set architecture. And that's the complete collection of all the unique different kinds of instructions and their formatting. So the instruction set architecture dictates all of the formats of each of the kinds of commands you can send. So those commands that are available to us, the programmer. So the choice of instructions that are exposed on a computer matter because they determine how quickly an operation can occur and the kinds of operations that can occur. It's also very closely tied to the kind of machine that you're implementing. So no two instruction sets are alike as long as the machine is any kind of different. People do try to standardize the kinds of operations you could see. So like the ALU will always contain some kind of arithmetic operations like add and subtract. But you can optimize on top of that. So like I mentioned, there could be specific floating point instructions, whether or not you have an FPU. But those would all be determined by this instruction set architecture, what the designer chooses to expose to the programmer. Another of the big takeaways is like the instruction set is intimately tied to the kind of machine. So if you're writing assembly, or if your program is written with a certain instruction set architecture, that will not be portable to another machine. Let's see. Yeah, generally all the instructions within the ISA contain a uniform length opcode. So either like 3 or 4 bits for small machines and maybe more for larger machines, and flexibly sized operands. So the operand fields within the instructions can vary in the number of bits that are necessary to represent each of the operands. It's also possible to have instructions that are more than one word in length. So instead of just an instruction that is storable in one memory register, maybe it takes 2 or even 4 to contain the entirety of the instruction. But again, that would be very machine specific. Let's see. Instructions are typically broken up into a couple different types. So computation, which usually routes directly to the ALU. Data movement, and that's copying or assigning bit fields from memory to registers or vice versa. And control, and that's control flow. So branching, jumping instructions, anything that is control unit specific. Let's see. Yeah, data movement can also access the I/O bus. There may or may not be dedicated instructions for, may or may not be dedicated instructions for that, depending on how the I/O bus is exposed. For some machines, that I/O bus is kind of tied to data memory. And what I mean by that is it could be memory mapped. So you could have like part of your data memory that signifies accessing something on the data bus. But that's also an implementation specific decision. So I know at Cal Poly, there are a couple different instruction sets that are taught. So I think the intro to, I think they call it computer organization, where they talk about a lot of these principles, uses LC3, which is a very simple instruction set. And I have a simulator that we can access. So if you have LC3 instructions that you already have written as a program, you can update this simulated memory here. So you could contain some instruction and data. This simulator will operate exactly how I discussed the fetch, decode, and execute cycle. So it'll fetch instructions from here, and you can watch the contents of the program counter, all of the multi-purpose registers, and the instruction register to see how the machine executes each of those instructions. I don't actually have any LC3 code written, otherwise I'd show you this working. But note that the simulator exists, and the link will be in the notes as I release them tonight. There are many instruction set architectures. So MIPS is another one that's taught at Cal Poly for some of the higher level classes in computer architecture. The one that we'll be talking about is AVR's instruction set architecture. So AVR is a specific computer architecture that also has a specific set of commands that you can give it. But the ones that are commonly used today are ARM, Hex86, and RISC-V, which I won't talk about. They're just different ways of organizing the machine to optimize for different kinds of performance and functionality. So yeah, we'll be talking about AVR later. So now we can program our computer, but it's going to be kind of a hassle because we need to know which parts of this bit field mean certain things. And I don't think anyone wants to keep recalling that these 4 bits mean opcode and which of the 4-bit configurations corresponds to the kind of opcode that they want to use. So to make things easier for humans, we invented assembly. Assembly is a programming language that's used to represent information that will be converted into bit fields. So the format that's natively stored on the machine, those raw bit fields, we call that machine language because they are natively interpretable by the machine. And so this is technically a language because we have a grammar. We have it's a set of bits that mean certain things in different formats. It's just hard to work with. So assembly is also a language, but it's much more it's much more parsable to the human brain. And the reason we do that is, again, so that we don't have to memorize a bunch of ones and zeros. And the method we use to do that is by converting opcodes into these 3 or 4 character commands that are much easier to memorize. So for instance, add is simply ADD. And that's how we would write it in our assembly file. It also provides utilities for interpreting operands. So typically you could, if your opcode specifically fetches information from registers, your specific assembly language implementation could have a short code to use for that register instead of having to memorize its index. Likewise, there are certain utilities that assembly provides for being able to interpret memory addresses much more easily. So if you have a register that contains memory address, you could either manually write that address, or you could say load from this short code that represents that address instead. Without assembly, our computer would look like this. We would have to manually input each bit and signify when that input is correct. I forget what this XKCD is, but oh yeah, something that is common in industry is people that have been working at the low level are kind of they're pretty zealous about working only at the low level, and so you'll see one of the common jokes is like, you know, if you're not working with the simplest or most close to computer tools that you can, then you're not a real programmer. Of course, this isn't the case. We invented programming and higher level languages to be able to optimize our speed of development. But there's something to be said about understanding, again, how the computer works at a native level. So it's possible to program everything using zeros and ones if you wanted to. But in practice, you don't want to do that. Yes, so assembly is a grammar of language reserved words, and those indicate the opcodes that are formed, that are used to form coherent commands that humans can interpret. Let's see. So there's those mnemonics for the opcodes. You can also reference information that's stored as program memory. So certain commands have a format where you can store what's called an immediate value. So something that's literally written into program memory and loaded directly. So if you have an add operation that works on immediates, so these literal values, you would store both of your operands into program memory. And accordingly, they'd have to be shorter integers that can fit in the entire program word. But it's possible to do an add operation without involving any registers. And assembly has an additional format for these like immediates. There are a bunch of other ways of addressing information to and from memory. And so the ways of representing the addresses is something that assembly can also help out with a lot. So once we have this assembly, it needs to be translated into machine code. And that's typically done with an external program called an assembler. The first assemblers, yes, had to be written using binary because assembly didn't exist. But as soon as you have that assembler, you have the ability to write in assembly and have that converted into machine code. And that's an immediate performance boost for being able to develop much more quickly. So all programmers really appreciate the people who developed these initial programs. Like I mentioned, the assembler translates these opcodes into machine language. So instead of the short 3 or 4 letter mnemonic, you get those bit values out. It also calculates the addresses that are necessary to store. So in assembly, you may like reference some other location in memory using one of the assembly specific formats. The assembler has to then convert that into an actual address that the machine can interpret. And this is kind of a complex operation because it depends a lot on what is in your assembly file. So if you insert a command somewhere, very likely the assembler will have to recompute the address that's actually intended by a specific instruction. And I can get into that with an example. But typically you would, after performing your assembler operation using your assembly file, you'll have this machine code, and then you'll have to store it on your device in your non-volatile memory, most likely, so that the machine can then interpret it. So an important point is that usually you aren't, it's dangerous to be able to change the program memory on the machine you're currently working with. So at least with microcontrollers, the common practice is to write your program, assemble it down into machine instructions, and then load it onto the non-volatile memory from an external device. If you are programming on an operating system like Windows, maybe that's not the case. Maybe you program on the machine that you're intending to target. But something like Windows is a lot higher level than working with an assembler directly. So for our purposes, we'll assume that all of our programming will be done on an external machine so that we don't have to worry about how that program memory is changed so much. So if your computer has a a modified Harvard architecture where the data and instruction memory are stored in separate areas, potentially on the same memory block. Then something after the assembler is also responsible for determining which memory segment to store this information in. So program memory will receive instructions, and data memory will have to receive raw data to be accessed by that set of instructions. Typically, the assembler is not doing that. What it will do is separate your assembly file into a data block and a programming or program memory block that can then be worked with. So the assembler is not responsible for assigning memory. That has to be a separate tool. And luckily for us, when working with microcontrollers, those tools are already very strongly built up. Sometimes the assembler can have like built-in functionality, but then it's technically more than an assembler. So to give you an example of what assembly actually looks like, this is a representation of the infamous Hello World program in assembly. So right off the bat, you'll note that there are something that doesn't look like an opcode. So this section command is a special assembly only keyword that dictates like where this chunk of memory that's beneath it will be loaded into. So this section .text is kind of an alias for program memory. So all of these we know are programs. And likewise, section .data is stored in data memory. So this is raw information that's stored as bits or bit fields, which can then be referenced. But this should never be loaded as commands. We also have this global command. I haven't worked with this like flavor of assembly before, but from my interpretation, that's kind of how the machine knows where to start. So we have start or underscore start, and this is a label. So this dictates, this gives us a handle to reference a specific memory address. So if this command, this move command, if that's stored in the address 0 of program memory, start becomes a handle that points to address 0. So if we, I don't actually know if this is going to be valid syntax, by the way, but load EAX with start. So let's say LD loads a register and EAX is a register. I'm storing the address of start in register A. So the address of start, again, is just whatever it's immediately written before in this assembly program. And this is why the address resolution gets a little hairy. Because if I inserted another command up here, well, rather, if I inserted a command up here, so add EAX EAB, the address that start points to is now 1 instead of 0. So anytime that you're modifying your program, you are likely pushing around addresses, which is why the assembler is so important, because it can evaluate what those addresses actually are. So you don't have to keep track of where this memory, this program memory address actually is. The assembler handles that for you. If you guys want to play around with this, we'll send that via chat. I have no idea what the complete instruction set architecture is for this, though, so you'll have to look that up. But I guess I can walk through what it actually does. Where is run? I'm blind, I don't actually see run. Execute. So NASM is presumably the assembler. Don't have to worry about this for now. We're taking all of the assembly files that are visible to this assembler and assembling them. Then it looks like they're loading this resulting machine language file to memory. I'm not sure exactly what these do. oh yeah, it is storing it in a file that's addressable by this name demo. So then we run demo, and it'll give us hello world. So let's examine why that happens. So for starters, we have this information that we're storing as data. So we have a string, which is a sequence of characters. And these are binary coded text. These are so likely ASCII. For anyone who doesn't know what ASCII is, it is a way of encoding human readable characters as binary values. So for instance, if we look here, capital A can be represented as decimal 65, which has its equivalent binary representation. So anything that is, any computer faculty that's designated to interpret information as characters uses some format akin to ASCII. There are some other formats, but at the low level, it's typically ASCII. Here's the site for reference. I don't actually have this in the notes anywhere, so just keep it at the top of your head. Here we have a literal character string. So it is a, it's literal because we are writing it into our assembly file, and this is what is intended to be stored. And we have the sequence of characters. So H would have its binary equivalent, E would have its binary equivalent, and so on. And at the very end, this is a special character. It's the null character, which terminates a string. That just happens to be a convention. I can get into what that means later, but it just means that this is end of string. So this MSG signifier likely indicates that this data field is a string, and DB, I think, just means we're storing data. This could be a special command that I'm not familiar with. Oh, I'm sorry. MSG is the handle that we're using to this data. That's right. So like start is a label that indicates an address. This handle indicates the address where this character string is stored. DB, that's the string command that indicates we're storing multiple bytes of information sequentially. Len is shorthand for length, and that's going to be another handle. So it's going to be the address of this information in data. EQU apparently gives us the length of a sequence of bits that's formatted as a string. So that sequence that's terminated at the end. I think this $sign character lets us address a value. I'm not actually certain. Again, not familiar with this flavor. But in summary, we are storing some data in the data section. And that data is a sequence of characters stored as raw binary values that equate to human readable characters. And we're storing the length of that sequence as its own variable. So when we actually move through our program, the first thing we're doing is moving memory. So this is loading from the data section. So this is a memory access operation where we're taking the length variable that we stored here. So we're accessing that memory address and loading its contents into, I'm guessing, register D. So this is one of those multi-purpose registers in the processing unit. So we're assigning that register this length value, and that length value better be the word length. The next instruction that we do is we load the first address value of this character sequence into register C. So these move commands only operate on, again, the word length. So we can only fetch basically one character at a time, or like 2 characters at a time, depending on what the word length actually is. I'm assuming this is an 8-bit machine. So if each of these characters is 8 bits, we get 1 at a time. These 2 commands, EBX and EAX, or sorry, these two move commands are setting up registers B and A. So that's specifically for the next operation that's going to happen. This int operation that signifies there's an interrupt occurring. So that's a special kind of control unit operation that kicks off a specific behavior. In this case, it's the command that lets us output to the console here. And its inputs are clearly the length of the string to output, the first address within that string, the place that we're going to try and send this information. So in this case, it's to the console, and the system call number. So that's the operation that we're doing based on this interrupt. You don't really need to know what all this means. This is just me walking through the code and indicating how assembly would sequentially run. So this int command, that's when the magic happens. That's how we get this string output to the console. And then this command, I'm guessing, returns from this operation. So that's system specific, machine specific. Something that isn't demonstrated here is branching and jumping. So if we had a different label, so assume this is valid assembly. It probably isn't for this file though. Register A, we're going to load that with an immediate 5. I don't know if this syntax is correct for this flavor of assembly, but so this means we're storing a literal 5 in register A, at least as I'm trying to write it. And how about a literal 3 into register B? And so this section of code adds 5 and 3 and stores it in register D, and that's it. Very simple. What we could do is somewhere below it, we could insert a jump command. So if we wanted to always do this operation, and this sequence of instructions is something that we're going to repeat throughout code, something that we could do is reuse it by having this be a labeled section of memory that we can jump to directly. So let's say we store let's say there's a register F, and what it signifies for us working with this routine is the instruction address that we need to jump back to after we do this routine. So let's say, let's store the program counter in F, jump to this routine. So let's see, actually, here, there we go. Very simple instruction. We have a labeled area. I'm gonna put this up here. Oops. So I've defined a new program area. So this is just 2 instructions and labeled it. So it's a designated area in memory that we can now access with this handle. The beauty of jump is that I can now access this clump of code anytime just by jumping to this this handle. So the way I've designed it, we're going to be adding the contents of register A, register B, and then storing it in register D. Typically, when you have a routine like this, you'll add many more commands than just one, but this is just an example. So I am first storing the current contents of the program counter in register F. So that dictates what the next instruction to load will be prior to this jump. I then make the jump directly into this routine. I perform the add, and then I jump to the register that was stored in F. So back to this program counter value. And that should get me to the next instruction here. So move something. So that is one example of control flow change. This is analogous to us doing like, for anyone who's programmed before, this is kind of equivalent to a function call. For anyone else, I'll get to what that means later. The other kind of command that isn't really demoed in the start code is branching. So let's say we want to do let's see. So it looks like this opcode doesn't actually exist in this flavor of assembly, but this would be a branching instruction that branches if equal. So if the last operation that occurred, the last arithmetic operation, produced a result that is equal to the contents of register A, then we would jump into this routine too. Otherwise, we just continue with the next instructions, move, something like that. So this branching instruction either lets us continue by incrementing the program counter, or if the condition is met that this branch indicates, we can now access some other routine in code. So we would change the program counter to whatever memory address routine 2 indicates. Of course, the specific format of the command and the opcode itself, so the mnemonic, will vary depending on your instruction set architecture. So I can't exactly give you a live demo of an assembly flavor that I'm not familiar with. So you can kind of see how this is, this lets us access the raw computer functionality, but it's a little limited in that we're constrained by where we can place these handles, what kind of memory addresses, and how we calculate them. And doing anything that's complex takes a lot of forethought and design. If you actually want to learn assembly, though, it is useful for doing like really performant operations. So if you program with a language that sits on top of assembly, as we'll get to, there's typically isn't a perfect mapping. So using that language means that there's a little bit of overhead that's necessary to manage the language constructs on top of assembly. And that just means your computer will end up being a little bit slower than if you were to write the program in assembly. However, your development time could be sped up by doing so. For applications that are really performance critical, so like real-time machines that need to be, that can't just like do an operation aside from what you care about, that have to do something well in real time as your other process executes. If you need something that does something like that, so like digital signal processing, if you don't have dedicated hardware for it, is almost always going to be written in assembly, or at least the functions exposed are likely written in assembly. If you are doing let's say like machine learning, the math libraries for that, if you don't have an FPU or a DSP core, that's also probably written in assembly. Likewise, assemblers and compilers are usually written in assembly as well. So if you're interested in learning it, there are a couple different flavors that you can learn. Hex86, I think, is the most common to program in assembly with today. Sometimes you see it with microcontrollers, again, if it's real time and performance critical. But there's a tutorial series at Tutorials Point that's actually pretty good for it. And I'll link that. Let's see. There are some other features that are common to computers that aren't necessarily standard. The first that I'd like to talk about is called the stack model. So in computer science, a stack is kind of this abstract representation of things. And the representation is a thing that contains information that has two operations, push and pop. And the constraints of these operations are push only adds to the top of the stack, and pop only takes from the top of the stack. So with a stack, it's impossible to access this element at the bottom without first accessing everything on top of it. The reason that's helpful is because it's directly representable in digital logic. So with memory, we could have something that's that indicates like the address of the last element in the stack and the first element in the stack. And we can just increment that address to represent the amount of data stored in the stack. And whenever we do a pop operation, we decrement that address. So it's simply representable, and it's particularly useful when we are using it to store information. So the nature of a stack, in that you can only access the top element, is helpful for representing when you have like a nesting of operation. So you have like a piece of information that depends on other pieces of information that come before it. Let's see. So yeah, the stack can natively be represented by bit fields and addresses. It's possible to do so in registers, but it's also possible to do so in memory. And for machines that are supporting this kind of operation, there's usually a dedicated stack somewhere. Typically, I've seen it implemented in RAM. So it'll be like at the bottom of the RAM. So the stack will grow upwards through all of random access memory, depending on how much stack space you end up using. And yeah, for machines that support stack-based operations, there will typically be instructions dedicated to push and pop. So the machine will keep track of your stack pointer, so the top of the stack, and it'll know when you've reached the bottom. So those dedicated instructions can be used to dump information onto the stack without violating it being a stack. So you can't necessarily access an arbitrary member using these instructions. So the computer will give us a native interface if it supports stack-based operations. But typically, those instructions aren't actually push and pop, because a lot of implementations end up using the stack for something very specific, and that's supporting this concept of a subroutine. Gotcha. Thank you, Alex. So a subroutine, like I hinted at with those assembly demos, is kind of just a reusable chunk of code. So it's a sequence of instructions that we'd like to refer to specifically as a group. And it has certain preconditions and postconditions. So things that have to be true for the subroutine to execute as we expect it to, and the conditions that we can expect it to produce given a certain set of input. And this is kind of like a mathematical function. So it takes input, gives us output optionally, or it could change some kind of state that we're representing using a finite state machine. But it's fundamentally a group of code that we can refer to by name. So in assembly, we use those labels, those handles, to indicate possible places where we can have subroutines stored. Labels don't have to be subroutines, but they can be. But the subroutine does need to have some kind of address that represents where those set of instructions are stored as a group. When we invoke a subroutine, it means basically we jump to it with our preconditions satisfied, and the program counter starts and executes the subroutine. Another way to refer to this is called calling the subroutine. And that may be familiar to programmers, again, because we call functions. So subroutines are very similar to functions, with some functions actually have more constraints than subroutines. So functions are one implementation of a subroutine. Let's see. So for stack-based machines specifically, if we call a subroutine, the machine needs to save the state of itself prior to jumping to the subroutine. So we save all of the control unit condition registers. We'll save the program counter as it stands prior to going into the subroutine. We might save like all the register values prior to entering the subroutine. And that's so that we can exit the subroutine and return to the conditions as they were prior to the subroutine executing. All of this is implementation specific. So the machine may behave in a different way, depending on how the computer architecture chooses to implement this behavior. But very commonly, if you have a stack-based machine that can work with subroutines, it exposes something called the stack frame. So in this example, we have these arbitrary objects that we're pushing and popping to and from the stack. These objects can be individual data words. So like if you have an 8-bit word on your machine, these could be 8-bit fields. But in the context of subroutines, these objects are actually sequences of bit fields. So you could have like a multi bit field set of information that you're pushing to the stack at one time. So what I'm calling the stack frame here is the set of information that we store prior to entering the subroutine. So if you would imagine this 2 is actually a chunk of bit fields. Maybe the first 3 indicate multi-purpose registers. The next one could be the program counter prior to entering the subroutine, and so on. So all that information could be pushed into the stack. The benefit of it being represented using a stack is that when we're in a subroutine, if you call another subroutine, then all we have to do is save the state within the first subroutine, enter the next subroutine, and all that information is stored in a sequential order that we can then access only after we've exited the latest subroutine call. So if you'd imagine 1 represents the, for this example at least, 1 could represent the state of the machine prior to entering any subroutines. Then we do a subroutine call, which stores the state of the machine as 2. We enter that subroutine and execute. And let's say that subroutine makes another call. We would now store our current state again as 3 and enter that subroutine. And by doing so, we can create complex sequences of repeatable instructions in groups. So if you have a subroutine that multiplies 2 numbers and one that adds 2 numbers, the one that multiplies 2 numbers could depend on addition. So you could just do a certain number of additions to equate to that multiplication. That would be a really dumb implementation because your machine likely supports multiplication. But for example's purposes, your multiplication subroutine could then call the addition subroutine a certain number of times. And every time that addition subroutine completes, the stack frame is popped from the stack. We return to the conditions indicated by that stack frame and continue on. So for the example of that multiplication implemented with add, what you would see is you would have the default stack frame, so the current state of the machine before calling any subroutines. We would call the multiplication subroutine, and then state this like 2 stack frame would stay there, and you would see the multiplication continuously adding and removing this stack frame 3, indicating that it's entering and exiting this add call at a certain number of times. And eventually, when the multiplication subroutine completes, this stack frame 2 would be popped. The machine state would return to the contents of that stack frame, and your instructions would just continue on. So again, this stack-based subroutine implementation is only offered on certain computers. It's most computers nowadays. But at the very beginning, and especially with like very small machines, so like 8-bit machines, wasn't always present. So most modern flavors of assembly have some kind of method of doing a subroutine call. That might be jump, or it might be a dedicated command. Let's see. Yeah, so the stack frame includes all the information necessary to return to the state of the machine prior to making the call. The most important of that being the program counter. Very likely when you do the jump call, it'll also increment that program counter prior to storing its state, just so that you don't return to doing the subroutine call again and again. After the subroutine completes, like I mentioned, we pop the entire stack frame off the stack and restore everything that it's representing. So all the temporary registers that are associated with the stack frame and the program counter for sure. So how we actually get information out of a subroutine varies depending on the computer. It could be stored on the stack as a value that sits like right on top of the last stack frame. So if we, there may be a certain command that could fetch that value directly, or we could store it in one of the processing units multi-purpose registers. But that's implementation specific, so it depends on the machine. It's also possible to kind of represent any machine virtually. So there's this modern development called WebAssembly. And I think it's really cool because it is a virtual machine that browsers support. So your web browser can run WebAssembly, which is pretty crazy to think about. It also means that this format, WebAssembly, is something that we could target using an FPGA. If we had it, if we designed our machine to take the WebAssembly native instruction set architecture, you could then put WebAssembly instructions in your program memory, in your data memory, and run WebAssembly on an FPGA. So WebAssembly is designed to be super portable because prior to that, browsers didn't really have, any kind of cross-platform or cross-browser capabilities. But this just kind of demonstrates the power of a stack machine. WebAssembly is a stack machine. And if you're interested in doing like web graphics, WebAssembly, I've heard, is going to be really big in that. The specifics of WebAssembly are interesting, and I'd recommend looking at it, but I'm not going to go into it really. So as I've hinted at, assembly isn't necessarily the only programming language. It is the one that has to interface with the computer. So if any other language is used, it has to be converted to assembly, which is then assembled into machine language. It's still used for, again, performance critical code, or if you're doing novel hardware. So like, say you have a new machine that you've implemented with a different kind of instruction set architecture. All of the operations that we need to use that machine flexibly and as a general computer have to be re-implemented using assembly. So that's another instance where you need to know the language. For the most part, programmers nowadays don't use it though, because there are much more efficient uses of time than managing bits directly. There are cases, as always. So next time I think we'll get into programming with C, how that developed on top of assembly, and get a bit more hands-on than we did today. So I think Alex had some kind of announcement he wanted to make.
Yeah, sweet. I guess first,